Hey, good afternoon. Today we're going to be talking about tolerances part 2. All right. Talk about some definitions. Limits. Limits are the maximum and minimum sizes shown by the tolerance dimensions. And that's why we have a limit tolerance, as we've discussed it, because it just gives us the highest and the lowest, or the upper limit and the lower limit. The upper limit equals the specified dimension plus the positive variance. So, right here, that's our positive variance. Well, what do we need to take from this then? The first thing is we've kind of introduced a new vocabulary or variance. We didn't really talk about this yesterday. Is that's the variance. That's how much it can vary. So that's not shouldn't be very hard to remember. The lower limit is the specified dimension. That's this. Oh, sorry. Specified dimensions, which is the 1.5, and then the negative variance. They say plus the negative variance or just subtract it, but that's this right here. All right, that's again what we're adding and subtracting is our variance. Yesterday I had you already calculating the tolerance. I called it the total tolerance, but it's the tolerance. That's from all the way from the upper limit minus the lower limit. So we've already done quite a bit of work here with the tolerance. So this shouldn't be very hard. But here's an example of it. You should do this example as well. Well, here's the number they've given us. So if we add the 0.05, we get 1.5 plus 0.05, which gives us 1.55. And if we subtract our variance here, this gives us 1.5 minus 0.05, which gives us 1.45. The tolerance then is when we take the 1.55 and subtract from it the 1.45. So that's what we were doing yesterday, and although yesterday I called it total tolerance, I'll do a better job here in the future of talking about the variance in the tolerances. All right, calculating tolerance. All right, again, this should be reviewed from yesterday. All this is adding the 0.05 to it one way, give us the positive or the upper limit, subtracting it, that gives us the lower limit, and when we subtract these two, that gives us the tolerance. General tolerances. All right, we talked about this yesterday in class, but this should be a good review here again. General tolerances, they're going to tell you, give you these X's, and they're going to stand for the number of decimal points. Again, one of the hardest things for students is when they see a number like this, 1.50. And they want to use this one right here because we want to ignore the zero. But there is a specific reason that the engineer or the person who drew the IDW, who made the drawing, made it 1.50 instead of 1.5. So we need to respect the fact that the zero is there, and this should be the one we use. All right. As a matter of fact, what they're telling you by adding this zero is that this is the tolerance that they want you to use, not that one. All right. So the zero does count when we're talking about the number of decimal places. Okay, we have three types of fit, and what we mean here is the first one is a clearance fit. Limits the size of mating parts so that a clearance always results when mating parts are assembled. All right, and what this really means is that the whole is bigger than the part. All right, it's always going to fit in there. All right, interference fit. This right here means that the whole is smaller than the part. And then we have a transition fit. It occurs when two mating parts can sometimes have a clearance fit and sometimes have an interference fit. Well, this would be if we have a hole, but we're trying to put something into it that maybe it comes at an angle. All right. And let's say this is the part for whatever reason. And this is the hole. Well, to start off with, all right, we're going to have a clearance fit because the hole here is bigger than the bottom of the part. So we start off with a clearance fit. As we start hammering this part down, we start to lose this gap. And all of a sudden now we start to run into an interference fit where the part up here, once that moves down, is going to be bigger than the hole. And that's what we call a transition fit. meaning part of it fits into the hole easily because it's a clearance fit, and once we get to a certain point, it becomes an interference fit because the part starts to hit the sides of the hole. I use the word hole up here. All right. I mean, that could be a hole. There's a spot that we're trying to fit them into. Um, hole is just any slot or anything you're trying to fit the two parts together into. So it does not mean that it has to be some round hole. That's not what I mean by using the word hole. This right here is a clearance, all right? And the reason we talk about this being a clearance is, notice that this hole at smallest is 10.15. This at biggest is 10.0. So this is always going to slide in and out of there very easily. This right here is what we call an interference, because this at smallest is 9.92 and this at biggest is 9.9. So this part is never going to fit and just slide in and out easily. You're going to have to put some type of force behind it to get it to fit in there. All right. So this is what we call an interference fit. All right, I've got some definitions for you here. The MMC, or the maximum material condition, is the condition of a part when it contains the largest amount of material. The MMC of an external feature, the length of a plate, is the upper limit of the dimension. The MMC of an internal feature, the diameter of the hole, is the lower limit of the dimension. The MMC is when it has the maximum material. All right, not when is the hole the biggest, but when does it have the maximum material. That's what's important here for the MMC. All right, the maximum material. All right, so for example, if I have a part here, if I make a small hole and I take this same part, pretending to the same sizes, and I have a big hole here, all right, well, when does this part have the most material, the most steel? Well, it's when it has the smallest hole. So that's what they're saying here. The MMC of an internal feature, the diameter hole, is the lower limit of the dimension. When they have the lower limit, right, when we have the hole being the smallest, is when we have the most material. The LMC is going to be just the opposite. All right, this is when we have the hard one, I know, for students then is when we have the cutouts here. We want the least material. Well, when are you going to have the least material? When the hole is the biggest. So how do we calculate the allowance? All right, the allowance. Well, allowance is the minimum clearance or maximum interference between parts. For a clearance fit, the allowance is the tightest possible fit between mating parts. Allowance, we take the MMC of the internal minus the MMC of the external. So it's internal minus external. Okay, so we have these two parts. All right, and this is a section view, so they've cut this in half. We know it's got this center line, so this is a circle and this is a circle here that's going to be fitting through. It's not a rectangle and a rectangular hole. If we want to calculate the allowance, we first have to take the MMC, the maximum material content of the internal feature. All right, well, when is this going to have the maximum material? When it's got the smallest hole. So that's why it's 10.15. When is this going to have the maximum material? When it has the biggest dimension, because there's nothing cut out. We want it to be the biggest. I mean, this one should be easiest. All right, when it's the biggest, that's when it has the most material. So we take the 10.15 minus the 10, and we have an allowance then of 0.15. Now I want you guys to look at this here. All right, go ahead and pause it and look at it for a few seconds and see if you can find the mistake. Right, because there is a mistake they make here. Did you find it? Well, again, we're trying to find the allowance. So the MMC of the internal feature, that's when the hole is going to be the smallest. Well, when's the hole the smallest? 9.85. So instead of using 9.9, it should be 9.85 minus, well, when's this going to have the most material? When it's 10. So what we should be getting then is a negative 0.15. So the allowance or maximum interference here is 0.15. Now, how do we know when it's allowance? Allowance is when we have a positive number. Interference is when we get a negative number. You do the exact same calculation, except you just got to think to yourself, is my answer positive or negative? Positive tells me I have an allowance, negative tells me I have an interference. And that's all there really is to it. Well, I'll leave you this note here about dimensional tolerance. In general, the more specified the dimension, the tighter the tolerance. Overly precise dimensions and overly tight tolerances increase manufacturing costs. Specify dimensions only to the precision and tolerance necessary for the part to function properly. Hey, there's a lot of information there. We're going to go over this a little bit more once you guys get done with your notes. I'll catch you on the flip side.